These are the answers to homework 5A. These are the definitions I would like you to know. And now to the questions. Number 1, the pressure of the first two gases below is determined with a manometer that is filled with mercury. The pressure of the last two gases below is determined with a manometer filled with silicone oil. Assuming an atmospheric pressure of 756 millimeters of mercury, determine the pressure of each gas in millimeters of mercury, torr, atmospheres, and pascals. So in our first manometer, where we assume the gas is being trapped by mercury, this is a close-ended manometer, which means on the right side where the mercury is in contact, it's in contact with a vacuum. There's no gas in there. That means the pressure exerted on this side of the mercury column is 0. Our gas is pushing on the left side of the mercury column, and because it's pushing the mercury column lower than the vacuum side, its pressure must be higher. So in the picture, make sure you can visualize that here. This mercury level here is lower than the mercury level up here. So the lower the mercury level, the more whatever's pushing on it is pushing harder. So because the difference in levels is what's important in a manometer, this is saying the gas is pushing 193 millimeters of mercury more than the vacuum. And if you know the vacuum's pressure is 0, that means the gas is pushing 193 millimeters of mercury more than 0 millimeters of mercury. So therefore, the pressure of this gas is 193 millimeters of mercury. If you want it in the following units, first torr. A torr is just the same thing as a millimeter of mercury. It was renamed. So if you have a pressure of 193 millimeters of mercury, it's the same as 193 torr. If you want the pressure in atmospheres, the equality statement you would need to use would be 1 atmosphere equals either 760.0 torr or 760.0 millimeters of mercury. They're the same. So if I take my 193 either torr or millimeters of mercury, multiplied by that equality statement with the torr on the bottom to cancel out, the pressure turns out to be 0.254 atmospheres. If you want the pressure in pascals, you'll need an equality statement concerning pascals. And we had learned that standard pressure is defined as either 1 atmosphere, 760 torr, 760 millimeters of mercury, or 101,325 pascals. Any two of those can be set equal to each other. So if I want to start with 193 torr, then the equality statement I can use is standard pressure of 760 torr equals standard pressure of 101,325 pascals, and that allows me to convert directly from torr to pascals. If I wanted to start with 0.254 atmospheres, I would have put 1 atmosphere on the bottom and 101,325 pascals on the top. I would get the exact same answer of 25,700 pascals. So that's your pressure in the first manometer. The second manometer also has a gas trapped by mercury, but in this case, the manometer is open. So therefore, what's being exerted on the mercury on the right side is the atmospheric pressure of 756 millimeters of mercury. When reading manometer, what's important is the difference in levels. And because the gas is pushing its mercury level down harder than the open atmosphere, the gas's pressure must be greater, exactly like in problem A. So the gas's pressure is 193 millimeters more than whatever the atmosphere's pressure is. So just like in A, we added 193 to the vacuum's pressure of 0. Now we're going to add 193 to the atmosphere's pressure of 756 millimeters because it's the atmosphere that's pushing on the mercury on the right side of the U-tube or the J-tube. So the pressure of the gas turns out to be, if you add those together, 949 millimeters of mercury. The answer in torr would be 949. The answer in atmospheres, 1.25. And the answer in pascals, 127,000. You could do the calculations the same way we did in part A. For part C, we now have a gas trapped by, in this case, silicone oil. And the silicone oil is different than mercury in that it has a different density. Now, how you read the manometer is the same. You take the difference in levels, and because the gas is pushing down on the oil harder than the vacuum is, we would say the gas pressure is 193 millimeters of silicone oil more than the vacuum's pressure of 0. But they don't want the pressure in millimeters of silicone oil. They want it in millimeters of mercury. So what I will need to do if I have a manometer where the liquid is not mercury is I'm going to have to convert the difference in levels, the 193 millimeters of silicone oil, into what it would be if this liquid in here were mercury instead. And the key to doing that is to know the densities of mercury and silicone oil and to compare those. So the density of mercury is 13.6 grams per milliliter. That means every milliliter of mercury would weigh 13.6 grams. And the density of the silicone oil is 1.3 grams per milliliter. So every milliliter weighs 1.30 grams. When a gas is supporting a column of a liquid, the gas can always support the exact same mass of any liquid. So if the gas is going to support a certain mass of silicone oil, it would support the exact same mass of mercury. And the way you figure out how they're related to each other is realizing that the more dense material, mercury, is going to require a less volume because it's so dense. The lower density material, silicone oil, is going to need a larger volume so that the two masses would be the same. And the really easy way to determine the equality statement between the two is just reversing their densities, because densities and volumes are inversely related. So if I flip the densities, 1.30 millimeters of mercury would have to have the exact same mass as 13.6 millimeters of the silicone oil. This gives me an equality statement now, so I can convert the 193 millimeter level difference of silicone oil in the third manometer into what it would be if it was mercury. So if I multiply the 193 millimeters of oil by the equality statement, 1.30 millimeters of mercury per 13.6 millimeters of oil, the millimeters of oil cancel out. That means that if the liquid were mercury instead, the difference in levels would only be 18.4 millimeters of mercury. So now that I have the difference in levels in the proper units, I can now add that to the pressure of the vacuum, which is 0, and that's going to give me the pressure of the gas that's trapped in the third manometer. It winds up being 18.4 millimeters of mercury. In torr, it would be 18.4. In atmospheres, 0.0243. And in pascals, 2,460. In our fourth manometer, we have the gas trapped again by silicone oil. This time it's an open-ended manometer, so what's pushing down on the right side of the silicone oil in the J tube is atmospheric pressure of 756 millimeters. Look at the picture now. The silicone oil is being pushed down further by the atmosphere than by the gas. That means the atmosphere's pressure is higher, or the gas's pressure is lower. So the gas's pressure is going to be less than the atmospheric pressure. It's going to be 756 millimeters of mercury minus the difference in the levels. But here the difference in the levels are 107 millimeters of silicone oil. So to get the same units as the atmospheric pressure, we'll convert the 107 millimeters of silicone oil into what it would be if it were mercury. And we use the same equality statement. 1.30 millimeters of mercury would have to equal 13.6 millimeters of oil. So I'll take the 107 millimeters of oil, multiply it by that conversion factor, and therefore the difference in levels of 107 millimeters of oil would be equivalent to 10.2 millimeters of mercury difference. And once again, because the oil level is higher on the gas side than the atmosphere side, that means the gas's pressure is less than the atmospheric pressure. So to calculate the pressure of the gas, I would take the atmospheric pressure of 756 millimeters of mercury, subtracted by the converted difference, which is now 10.2 millimeters of mercury. Units are the same. Subtract the 2. The answer comes out rounded to the ones place, 746 millimeters of mercury. In torr, that would be 746. In atmospheres, 0.981. And in pascals, 99,400. Question number 2. Given the following data for properties X and Y, I would like you to prepare 4 graphs. The first one, I want you to graph Y versus X. So this would require some graph paper for you to do. And so if I have a piece of graph paper that looks like this, and I take a look at the data that's being asked to be graphed, I'm going to graph the X values on the X-axis, the Y values on the Y-axis. When you make a graph, it's important how you set up each division along the X and the Y-axis. And if we start on the X-axis here, you have to make sure every single division along this X-axis is equivalent. So I might start right here with 0 and go 10, 20, 30, 40, 50, etc. What I absolutely would not do is write 29, 35, 44 and put 29 here, 35 here, and 44 there. And if you do that, the individual divisions in the graph are not evenly spaced and you will not get a proper representation of these two phenomena. The same thing has to be true on the y-axis. I have to evenly space out every division so they're all equal. So if I started with 0 here and I made this 10, this has to be 20, then 30, then 40, then 50, etc. I would not put 16 here, then 20 here, then 24 there. That would come up with a skewed graph that wouldn't be proportional. So with my x and y values, I'm going to make each individual division a unit of 1 so that each of the major divisions stand for 10. And on the x-axis, I'm going to make each individual division stand for 1 so the major divisions stand for 10. And now, just like you did back in Algebra 1 in the old days, you're going to plot the x-coordinate and the y-coordinate of each point and plot it on the graph. 87, 16, 70, 20, 58, 24, 44, 32, 35, 40, 29, 48. This relationship is not a linear relationship, and in fact, it looks like it's curving. And if it were to continue in both directions, it looks like it would asymptotically approach the y-axis and the x-axis. That's the characteristic graph of an inverse relationship. And in science, we actually like to have all graphs that are published to be linear graphs. And so we're going to look at 3 different ways where we can take this XY relationship, which is definitely not linear, it's actually hyperbolic, and we're going to try to graph it as a line. And that's what graphs B, C, and D are demonstrating to you. So in part B, it asks you to graph y versus 1 over x. So for you to do that, you're going to have to take all the x values, 87, 70, 58, etc., take their reciprocals and calculate the decimal equivalent. So 1 over 87 equals something, 1 over 70 equals something, 1 over 58 equals something, and you actually are going to have to calculate those because you can't graph 1 over 87, 1 over 70, and 1 over 58 on a piece of graph paper like this. So I've actually calculated the reciprocal of all the x values, and you can see they're fairly microscopic. So if I'm going to try to make my x and y axis here, and in this case, the y axis will be graphing the y value, the x axis will be graphing 1 over x. The y values, I can once again make each individual division worth 1 and the major divisions 10, 20, 30, 40, 50, etc. But I can't do that on the x-axis because if I make this 0 and this 10, well, this is 1 right here. Every single point on the graph will be between these two itsy-bitsy spaces. The whole graph will be microscopically thin. So you can make the divisions on the x-axis different than divisions on the y-axis. And if I notice my 1 over x values go up to a little close to 0.04, I can maybe make this 0, this 0.01, 0.02, 0.03, 0.04, 0.05, and that would pretty much spread out the values across the x-axis fairly well. So if I do that, now once again, I'm going to plot my coordinate points. So the first one is 0.011, 16, 0.014, 20, 0.017, 24, 0.023, 32, 0.029, 40, and 0.034, 48. So by taking the reciprocal of one of the two variables, you can see that a hyperbolic graph of two variables can be made to be graphed linearly just by taking the reciprocal of one of the variables. Let's go to part C. Part C asks you to graph the log of y versus the log of x. So this will require you to calculate the base 10 logarithm of all of the x values and all of the y values. And so that's what I've done here by taking their base 10 logarithms. In this case, when I set up the x and y axis, which will be graphing log of x and log of y, the numbers actually range from about 1 to 2. So there's no rule in mathematics that the lowest point in your graph has to be 0. I can actually start this as 1 if I want and go 1.1, 1.2, 1.3, 1.4 like that, if I can fit all my points along here, and the same thing on the x-axis. So what I'm going to do is start, the bottom value is 1, and make each major division a 0.1. On the x-axis, I'll do the same thing, and now I can actually maximize the amount of space on the graph I'm using. So the first point, coordinate pair, 1.94 and 1.20 would plot here. The next point, actually, I think what I did is I actually did the bottom one first. So it's 1.46 and 1.68, then 1.54, 1.60, 1.64, 1.51, 1.76, 1.38, 1.85, 1.30, and 1.94, 1.20. So just a different technique now to take data which is normally hyperbolic and graph it so that the points will come out in a straight line. You can do that by graphing the logarithm of each of the different variables. The final way to do this is to graph the product of x times y versus x. So I'm going to have to multiply x times y together and see what it makes. Each of these numbers given in the data today are each two significant figures. So when I multiply them together, I'm going to get a two significant figure number. So that means for each set, the 87 times 16, the 70 times 20, the 58 times 24, et cetera, I'm going to wind up getting a two significant figure number. So even though they bounce around from 1394 to 1406 to two significant figures, they all come out the same value. So on the y-axis, I can pretty much spread it out any way I want. I just need to get 1400 on there. And the x-axis, because once again, the numbers range from close to 0 to 90, I'm going to make each major division 10. So when I graph the first point, where x is 87 and y is 1400, the point would go here. For my second coordinate set, 70, 1400, it would go here. And my third set, 58, 1400 would go here. And maybe you can see why we do this now, because if the product of x times y is always the same number, that means your y value will always be a constant. So every point you plot will be a horizontal line at exactly 1400.